Well, it's time. Welcome to an exciting digital design class. My name is Professor Lyon, and until or unless a vaccine becomes available, I am going to be teaching remotely this semester, which means that we'll be starting on time with this section at 12:30. Monday and Thursday, and we'll use the same Zoom link that you're using now. And I'll be recording these sessions, and I'll try and do a similar, if not identical, section that will follow this one, starting at about, I think it's 2 o'clock. And in fact, what we'll do is we'll take a quick tour through the syllabus, and yes, indeed, you can see there's another section which you can join, and you don't need my permission to join it. We'll have the same homework assignments, and we'll try and cover the same material. And that is also online with Zoom. So that's a thing, right? So you pick your section. At some point, if we go back onto campus, we'll actually have to stick to the sections because things are a little bit crowded. But for now, it kind of doesn't matter. As far as rules of the course are concerned with Zoom, I would ask that you keep your microphone muted until or unless you have a question, at which point unmute the microphone and jump right in. That's totally okay. I'm going to try and keep my chat window open as well. Some people prefer to issue a message via chat, and you can certainly do that. And if I miss it, you got to chime in and ping me because I may be in the middle of a problem and I just didn't watch it. But I'm trying to keep a chat screen open on a different screen here than the one you're seeing so that I can keep track of questions as they come in. And I just assume you interrupt me as anything because I don't see any point in letting questions fester. So best time to ask a question is when you have it. I'm going to adjust, I'm going to mess with my volume right now because things are not coming in clearly here. I'm not quite sure why. Maybe testing. That's better. Oh, okay. How about this? I guess I don't get to just adjust this. All right. Well, hopefully everybody can hear me clearly. And if you can't, do speak up. So let me sort of go through the course a little bit. This course is called Digital Electronics, and then there's this word in here, design. And so what does that mean? It means we're going to be doing a little engineering design, which you may not have seen in some of your other courses. And that design is going to mean starting from open-ended English language statements about the problem you're intending to solve, and then coming up with designs which may be unique to you. I'm going to skip over the course learning goals and the Bloom taxonomy, which you can read and grunt. There's a course textbook, and at this point, I'm hoping everybody has it. It's available for you, available used, and the used version is the first edition, and it's relatively inexpensive. I think you can still get it on Amazon inexpensively. And if I were to use Dr. Google here, I would think, oh, it's trying to add it. Well, let's go to Amazon and get it. Really? Oops. So that's the new edition, and here is the older edition. And it looks like it's getting harder and harder to find. Oh no, here it is. So it's gotten a little bit more expensive than when I first cited it, but it looks like there's 19 used copies from $8.97, not including shipping. So it's not too terribly expensive. And everybody should be able to get a copy of this book, I should think. And we will be using it. We will be using it. Let's see. What else do we need to know about this course? My schedule. This is the course webpage. If you click on the docjava.com webpage, you'll come to here. And then if you click on courseware, you can find Digital Design 1. And there's the book. I guess I could have gone there to begin with. There's new Vimeo packaging available, which is available here. And then there's also individual lectures that are broken out. And some of them are broken out by topic. So you can see lectures that are, I would call them longish lectures, like from 12:30 to 1:45 or something like this, like what we'll be doing. And then there's lectures that are broken out by subject area, and they may be perhaps little 5 or 10 minute lessons. And so if there's something specific that you want to learn related perhaps to your homework, you can do that. And so this will enable you to just like go in and click on Johnson counter and then learn how to design a Johnson counter without having to watch a lecture that goes on for 2 hours or something, which, people wouldn't like necessarily want to see. So I have individual subjects in here, a few videos which you can watch, and they're very fun. And if you take a look at some of the links in the homework, you'll see that there are a few different, I'll call it active learning activities that you can engage in. But before I get into that, I want to finish the syllabus. So we've got these office hours. I got to say that office hours don't have a whole lot of meaning in the virtual world. If you want to meet with me, I'll meet with you. Just, appointment required, because I'm not going to sit around in Zoom waiting for somebody to show up. That doesn't kind of make sense. So shoot me an email. We'll make an appointment, and we'll get together on Zoom and or by phone, and then we'll coordinate. Courses I'm offering include 2 sections of this digital design course, formerly known as CR 245 and now known as CPEG 2245, because that's better, right? And then I'm also doing a computer networks programming course, cross-listed at the graduate level, and we need students in that class. So what I would say is, if you're at all interested, please reach out to me, because we need to get people registered in that course like now, or they're going to kick us out to the curb and give me a different teaching assignment or something like this. Here's the grading. Everything counts for a third, which basically means homework counts. I mean, if you think about it, if you don't do homework and all you did was get 100 on the midterm and the final, you're basically getting a 66 in the course, which is pretty much just a D. So do your homework. It's good for you. And then the computer will cut you off at the deadline. It's programmed and it's heartless. And if you need to appeal, I will certainly take pity on you and try and get you in. But if you wait till the end of the semester to submit all your homeworks, I'll just say no, you can't do that. So try and keep up with the homeworks. We'll have one every week, and we'll try and make it so that you have at least a week to do the homework. Let's see now. Attendance attendance is kind of meaningless in the virtual world. I think what's going to happen is we'll record everything, and it's better to be synchronous, especially if you've got questions during the time when we're having a session. Then you can ask your questions, and that's kind of why I'm here, is to help you. Here are some topics by week. I don't know how strict we'll be in terms of sticking to that. And that's the syllabus. Are there any questions about the syllabus? So bottom line, this is a distance learning course until I can get a vaccine, because last semester we had 600 and a fraction people infected, which was kind of a bummer, actually. So let's take a look at a digital computer. Here's one. It's made out of wood. I like this because it's a simulator. Let's add 4 and 2 to make 6 and load it into our machine. So now we have 4 and 6. Now what happens if we add 4 to 6? We should get 10. Let's find out. And here we have 8 plus 2, and that's 10. So this is interesting from a few different points of view. First, it's digital. Second, it's binary. It's using only 2 bits, with the marbles representing either a 1 or lack of a marble would be a 0. It is a computer. It's doing computations. Well, at the very least, it's a calculator. Let's add 3 to 10 and see if we get 13. And what do we got? 8 plus 12 plus 1 is 13, so that's good. Now what we'll do is we'll add, what shall we add? This is not coming out. Oh, there it goes. We will add 15 and see what happens. And that's kind of cool, right? Because now what? We got 16 plus 8 plus 4, which presumably is 28 or something like this. So that's kind of cool, actually. This is doing kind of what you would expect a digital adder to do, only it's doing it with pure mechanics. And in fact, you can buy these things, but when they make them out of wood, it's a craft that requires a lot of hand labor, and they come in at about a couple $100. So I haven't bought one yet. And I didn't feel the need to buy one because I have this, and that's good enough for me. But if you ever want like a nice wooden one, they'll make one for you, which is kind of cool, actually. So you can make calculators out of wood and marbles. I've built little computers out of paper clips and light bulbs and plastic and springs. And it's kind of an interesting idea. When you do digital design, if you leave off the term electronics, you get a lot of different ways to implement these things. And that's kind of an interesting idea. Let's see if we can bring back the syllabus here. Working on it. There it is. Yeah. So because we're doing things with electronics, we would expect stuff to work with some sort of an electrical switch. And the question of exactly how that electrical switch works, we haven't really tried to address yet. And so that's an interesting idea. And their first homework assignment is on this first topic that's listed here, numbering systems and codes. And so what I'll do is try and give you a brief overview of some basic ideas involving numbering systems and codes, unless there are some questions that you might like to ask. Any questions? So let's start off with this little guy here. I'm going to try And now that I think about it, maybe what we'll do, let's quit out of presenter and we'll see if we can get Zoom to actually display what's on the camera. I think it can do that. We'll just have it start video. There. And then I'm trying to show that video full screen. Do you see it full screen?
No, not full screen.
All right, let me see if I can adjust my Zoom headings. Bear with me just a moment. View. Switch camera. Switch camera. So it isn't full screen. All right, well then let's stop the video. And I'll go back to IPVO, which is where we were to begin with, and see if we can get that to work. So are you seeing the video now? You may not be. Yes, yeah. You can see this part right here.
Yeah.
Oh, good. Okay, just checking. All right. So what I wanted to do was get away from PowerPoints because PowerPoints corrupt and power corrupts and blah, 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 blah. Don't want PowerPoints. So let's think about numbering systems. I'm going to start with one called Radix equals 10, which we have as a basic numbering system known as decimal. And in decimal, what we do is we express numbers like 101 using a base, which we call 10. That's the radix right in through there. And when we write out 101, 101, we write out that it's 1 times 10 to the 2 plus 0 times 10 to the 1 plus 1 times 10 to the 0. And that's equal to 101 base 10. And that's an interesting idea because the base over in here is the base of the exponent. And the exponent represents the position of the symbol. And the number of symbols is actually equal to the base. And we have symbols numbered 0 through 9. There's another, I'll call it numbering system, base 2, which we term binary, bi meaning 2, nary meaning number. So it's a 2-number system, which has 2 symbols, 0 and 1. And as it happens, if we take the string 101 and represent it with base 2, it comes out to be a rather different value because now we have 1 times the base, which is 2, raised to the 0, 1, 2 power, plus 0 times 2 raised to the 1 power, plus 1 times 2 raised to the 0 power. Well, this is a really different number, right? Because 2 to the 2 is like 4, and 2 to the 0 is 1, and 1 plus 4 is 5, base 10. So what I see here is a really different value from 101. If somebody gives you $101 and you say, yeah, is that base 10? You know, you say, well, wait a minute. What are you talking about? But if it is base 2, they're really only giving you $5. But if it's base 10, they're giving you $101. And you can see these things are really different numbers. They cost different amounts of money when you're using them to represent something that you have to pay for. This system for representing the numbers is known as positional notation. and it works for every base, which means any numbering system. Let's try it again. Only this time, we're going to have 1, 0, 1, and it's going to be base 16. That has a special name. This is radix equal 16, and we call this, anybody know what this is called? This is
Hexadecimal.
That's exactly right. Hexadecimal. And so there's 16 symbols, 0 through 15, or actually 0 through 9, and then A, B, C, D, E, and F, because A, B, C, D, E, and F are 6 more symbols, right? So if you look at the numbers, it goes this way. 1 times 16, see the base has changed now, 0, 1, 2, plus 0 times 16 to the 1, plus 1 times 16 to the 0. A completely different number, right? Because now what? I got 0 times whatever is 0. I got 16 squared, which is probably something like 256. And 256 plus 1, because 16 to the 0 is 1, and 1 times 1 is 1, is going to give me 257 base 10. And now we have done 3 different bases, 10, 2, and 16. There's another base, a common base. And this one is called radix equals 8. Anybody know what that's called?
Octal.
That is octal. That is correct. So then in octal, if I said, well, here's the number 101, base 8. I've changed the base again. Now I have 1 times 8 to the 2 plus 0 times 8 to the 1 plus 1 times 8 to the 0 equals, and now I have 8 times 8 is 64 plus 1 is equal to 65. Base 10. And in fact, what we do is we say something like 101 base 8. We do not say 101 base 8, because it's very clear 101 base 8 is a totally different number than 101 base 16, or than 101 base 2, or than 101 base 10. These are completely different values. And as a result, we really need to know the base before we can proceed to figure out what the values are going to be. Are there other bases available to us? The answer is yes, there are, but we don't typically use them in this course. If you want to, you can encode a binary file using Unix to Unix encoding. And that uses radix equals 64. And the 64 symbols come from the ASCII, or American Standard Code for Information Interchange. And so they'll use A through Z, uppercase and lowercase. They'll use all the punctuations, exclamation point, @ pound sign, $sign, percentage sign, all of them. 64 different symbols. And then those 64 symbols, if they're equiprobable, will be used to represent the binary numbers that are in some sort of a blob, let's say your Excel spreadsheet or a JPEG image or something like this. So yeah, in this, when it's encoding, a binary blob will allow a mail transfer agent, known as an MTA, to transfer the binary data as though it were text, because it is text. It's just that you have to identify what kind of a text it is so that it can be decoded at the receiver properly. So it'll say, oh, you need a helper application for this PDF file, you need Acrobat, and here's this binary blob converted to PDF and then open Acrobat. And either your browser or your mail client will handle that decoding process. So in effect, other bases are commonly available and commonly used, but these are the ones we care about in this class: binary, decimal, hexadecimal, and octal. And that's it. We don't normally care about other bases. How am I doing so far? So positional notation, PN, can convert to base 10, base 8, base 16, or base 2. Oops, I'm off the screen. And that's fairly clear. But it's important for us to be able to go back and forth. In other words, if I'm in base 10, I'd like to be able to convert to base 2, or base 8, or base 16. And so what we need to do is we need to find a way to do that. Right? So positional notation will allow me to take any string in any base and convert it to base 10. But suppose I want to start with something a little bit different. Suppose I said to you, well, I've got this number and it's in base 10. I'll call it 101, base 10. And I want to convert it into some other string in base 2 such that the two numbers are equivalent in value, even though they don't appear to be equivalent. How would I do that? How do I take 101 and make it into a binary string? Because I need a binary string in order to encode it for the computer, because the computer only knows about switches, and the switches are either on or they're off, and that's it. That's all we know. It's either true or false. Any ideas? Let me take a stab at it then. I'm going to take 2 and 101 base 10, and we're going to try to divide it by 2, and we'll get 5 with 0 and 1 left over. We'll do it again, and we'll get 25 with nothing left over. And we'll do it again, and we'll get 1, 2 with 1 left over. And we'll do it again, and we'll get 6 with nothing left over. And we'll do it again, and we'll get 3 with nothing left over. We'll do it again, and we'll get 1 with 1 left over. And we'll do it again, and we'll get 0 with 1 left over. The most significant bit is at the bottom. The least significant bit is at the top. And so what we say is, reading from bottom to top, 1, 1, 0, 0, 1, 0, 1, base 2 is going to be equal to 101. Seems as though this camera is wanting to automatically focus. I think it's pointing at, it's focusing on my finger. You know, it's like, here, I point at this. I say, look at the moon. And it says, oh, very nice finger. And I say, no, 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 look at the moon. So this is an interesting artifact. We can rewrite this in positional notation. Let's take a look. 0, 1, 2, 3, 4, 5, 6. So those are the positions. So I have 1 times 2 to the 6 plus 1 times 2 to the 5 plus 0 times 2 to the 4 plus 0 times 2 to the 3 plus 1 times 2 to the 2 plus 1 times 2 to the 0. And now I have a number. 2 to the 4 is 4. 2 to the 5 is going to be 32. 2 to the 6, that should be 64. And 64 plus 32 is 696 plus 4 gives me 100 plus 1 is going to give me 101. And that is correct. That's what we expected. So this is a way, using so-called repeated division, in order to be able to take a base 10 number and convert it into a base 2 number. And this positional notation is my way of validating that the base 2 number is a correct representation of the base 10 number. How does that grab you? So if you want to convert from radix 10 into radix 2, you can do so using a technique called repeated division. But if you want to go from radix 2 back to radix 10, you do it with positional notation. And so now we can see that different technique is being used when we go from radix 10 to radix 2 than if we want to go from radix 2 back to radix 10. So that's cool. What if I want to go from radix 2 to radix 8? Well, radix 8 is base 8, and base 8 represents numbers that are 0 through 7. In binary, we write and then what we do over in here is we say R equals 8 versus R equals 2. In other words, this is a mechanism of counting. When we add 0, 0, 0 plus 1, the 1 comes into the least significant place. But if I add 1 to 0, 0, 1, 1 plus 1 is equal to 0, carry the 1, because we've exceeded the radix. Add another 1, and you get 1, 1. Add another 1, and it's 0, carry the 1, 0, carry the 1, and finally you get a 1 out in here. And so in effect, by adding 1 in here, you can see where the 1 comes in, and then the least significant bits in here are repeating the pattern that we saw in the least significant bits over there. So that's kind of how we count in binary. Now, over in here, what I'd like to do is group by 3. So each octal digit over in here represents 3 bits. So if I take 3 bits at a time, what I can do is I can take 101, which is from here, and write in 5. 100, which is from over here, and write in 4. And here's a 1 that represents octal digit 1. And now in octal, I can write 1, 4, 5, base 8. And now to go to positional notation, I can write 1 times 8, that's the base, to the 0, 1, 2, plus 4 times 8 to the 1, plus 5 times 8 to the 0. 8 to the 2 is 64. 8 to the 1 is 8, and 4 times 8 is 32. And 8 to the 0 is 1, and 5 plus times 1 is equal to 5. And now I can write that 64 plus 92 is equal to 96. And I add 5 to that, and I get 5 plus 6 is equal to 1, carry the 1, put the 1 over here, and I get 101, base 10. So that shows that 145, base 8, is indeed equal to 101, base 10. So to go from radix 2 to radix 8, I have group by 3. And to go from radix 8 back to radix 10, I use positional notation. And that allows us access to a mechanism for converting to base 8 by using the intermediate form radix 2 or base 2 or binary. So I go to base 8 by going through binary because dividing by 2 is easier than dividing by 8. I could have done it with repeated division by 8, but I chose not to because dividing by 2 is easy, and I like easy because easy is better than hard.
Professor,
Yes.
what did you write above the R2 to radix 8? Like GB?
That's group by 3.
Okay.
I ran out of space, so I abbreviated. Sorry about that.
Uh,
Let's see. Yes.
Professor, I also have a question.
Sure, go for it.
Just above, when you did the Radix 10 to Radix 2 up there, what did you write above, like for the position of the 1100101?
Yes, so these are the numbers of the positions. So that's position 0, position 1, position 2, position 3, position 4, position 5, and position 6.
Oh, okay.
I use these numbers for my exponents on the base when I write out in positional notation. So because this is 1 times 2 to the 6 because it's in the 6th place.
Oh, okay.
This is 1 times 2 to the 5 because it's in the 5th place. And I skipped the zeros because anything times 0 is 0. And then, unless you have a quantum computer, in which case I'm not quite sure what it is. And then you have 1 times 2 to the 2, and I left off the 1 because 2 to the 2 is 4, and 2 to the 2 times 1 is still 2 to the 2. And then I left off the 0 here, and then I wrote 1 times 2 to the 0 is 1, so I figured that's 1. And I just put the 1 down.
Okay, thank you.
Sure. So now, in this one little page, we've got Radix 10 to Radix 2, decimal to binary using repeated division, binary back to decimal using positional notation, decimal to octal using repeated division into binary, and then group by 3 to give me octal. And then I go back from octal to decimal using positional notation. Yeah, we have another base we haven't thought about yet, right? Let's look at this binary number again.
Professor, I had a quick question.
Yes, sure.
So when you wrote positional notation on the previous page, so the one before this, what did you write next to it? Because, yeah, I was just a little confused, I guess, with. So with positional notation, it can be applied to bases 10, 8, 16, and 2. That's what you meant by that.
Yeah,
Oh, okay.
what this means is that if I have a decimal, a binary, a hexadecimal, or an octal number, and I want to use a mechanism to convert them to decimal, I can use positional notation. But so now what I'm looking to do is go from bases like decimal into bases like binary, hexadecimal, and octal. In other words, I want to go the other way. So far, positional notation will let me arrive at decimal. But if I start with decimal, I need to go into these other numbering systems. And one thing I found out with this particular exercise was that if I wanted to go from decimal to binary, I needed repeated division. And if I wanted to go from binary to base 8, I needed to group by 3. But if I wanted to go from binary, let's take this, let's get a fresh piece of paper because that's always good. Let's take this binary number that we've been working with, 1100101 in base 2, which is equal to 101 base 10. And let's see what we can do to turn it into a base 16 number. Now, base 16, also known as hexadecimal, is numbered typically like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and then F. These symbols number 0 through 15, and there are 16 symbols, including 0. If I were to take these symbols and write them out in binary, I would need 4 bits. it's a little bit sloppy. So let me go to a thinner pen. Now, because we've gone to this bit, these bits in through here will be repeated, and then the rest will have a 1 in the most significant bit. So in other words, if you were to split this list right in through here, this section is mirrored right there. And not even mirrored, it's just copied right there. And the only difference between these rows and those rows is this most significant bit where the 1 is set. And these are the binary numbers, and you need 4 bits for each of the hexadecimal symbols. Thus, we, instead of grouping by 3, we group by 4. And now you can look this up, 0101, and it comes out to be a number like 5. You look this one up, 110, which is right there, comes out to be a number like 6. So now we can say this must be equal to 65 base 16. 65 base 16. How do we validate that? And the answer is positional notation. So now we take 6 times 10 to the 01 plus, oh, sorry, the base is 16. Forgive my blemish here. 6 times 16 to the 01 plus 5 times 16 to the 0. So now, given these two numbers, I should be able to get a simplification. 6 times 16 plus 16 to the 0 is 1, so that's plus 5. And then, can you see this calculator? I guess you can. 6 times 16 is, it's sort of, you can see it's 96. And so I'll just throw that in there. I like the nice big numbers because you can see it. So that's 96 plus 5, which is 1, carry the 1. And now I have 101, which is correct. That's what we wanted. So 65 base 16 is equal to 101 base 10. So now I can complete my little diagram for doing computations. If I'm in Radix 10 and I want to go to Radix 2, I can use repeated division. If I want to go from Radix 2 back to Radix 10, I can use positional notation. If I want to go from Radix 2 to Radix 8, which is octal, I can use group by 3, GB3. I wrote an abbreviation there. If I want to go from octal back to decimal, I can use positional notation. If I want to go from binary to base 16, that's Radix 16, I can do group by 4, which is relatively simple computationally. I just group from left to right 4 symbols at a time. And if I want to go from base 16 back to decimal, I can use positional notation, which is right in through here. And now I can convert to base 16 or to base 8 or to base 2. And all I need is repeated division and either grouping by 3 or grouping by 4 for base 8 or base 16 respectively. And I can always go back using positional notation to decimal. And that's everything you needed to know about numbering systems ever. Well, in this course. With the possible exception of fractions, which we're not going to get into. So for whole numbers, what do you think of that? Who got confused? Let's have a looky-loo at some of the homework assignment and see if there's anything in there. Somebody want to ask any questions about any specific homework assignment, or shall I just do the first one and we'll see how that works out for us? You all right? Let's do problem.
Yeah, you
Go ahead.
yeah, you can do the first one and we can go from there.
Yeah, let's do the first one. It's a rather long homework, but the exercises are very good because it lets you, start to think about numbering systems and get kind of good at it. So here we are, homework number 1, problem 1, digital design 1. Everything's got a 1 in it. It's either 1 or 0. Hey, I'm a computer engineer. What can I say? So it says here 186. This number is meaningless until we know the base. It says base 10. So that's a decimal number, 186. And we want to convert it into some number base 2. And according to my little cheat sheet over here, my summary, to go from base 10 to base 2, I need repeated division. So what I'll do over in here is I will swap to a pen because I find it a little bit easier to write with a pen than with a marker. And I'm going to write 186, 9, 3, 0 left over, 4, carry 1, 6, 1 left over. If I make any stupid mistakes in division, just stop me before I get too embarrassed. And that will happen. So I'll say, hey, Professor Lyon can't divide by 2. What's the matter with him? I'll say, well, it's old age or something. I don't know. So then here we go. 5, 1 left over. 2, 1 left over. 2, 1 with nothing left over. 2, 0 with 1 left over. And so now if we write this out, what we get is 1, writing from the bottom to the top, that's your most significant bit because it took longest to get it. 1, 0, 3 ones, 0, 1, 0, base 2. So that sounds like a correct choice. 1, 0, 1, 1, 0, 1, 0. And then what you do is you take a look over here and look at that. It's 1, 0, 1, 1, 0, 1, 0. And that is a correct answer. So apparently Professor Lyon does remember how to divide by 2. Yay. So that's good. That's good. It's very important. So this is the answer to question 1, homework 1. What say you? Who got confused by this?
I have a question. How did you get the first 1? 1, 0, 1.
This one here comes from here. So I wrote that I start from the bottom and I work my way up and go left to right. If you go the other way, the whole thing will be wrong and backwards. It's a common beginner mistake to start from the top and start writing left to right from the top. But this is your least significant bit, and this is your most significant bit, and most significant bits go on the left. So that's the way, well, it's true also. Most significant symbols go on the left when you're dealing with decimal as well, right? Because that's the hundreds, that's the 80s, and well, that's the 10s, and that's the 1s. So yeah, that's why we did that. So next question. Any other questions here? Want to try another one? Let's do another one.
Let's do it.
Question 2 says, convert the following number to the desired base. We start with 21014, base 10, and our goal is to make some sort of binary number. And naturally enough, the last time we did it, we used repeated division. This time is no different. So I write down 214, divide by 2. I get 107 with 0 left over. Divide by 2, I get 5, 3 with 1 left over. Divide by 2, I get 2, 6 with 1 left over. Divide by 2, I get 1. 3 with 0 left over. Divide by 2, I get 6 with 1 left over. Divide by 2, I get 3 with 0 left over. Divide by 2, I get 1 with 1 left over. Divide by 2, I get 0 with 1 left over. And now I write out a number starting at the bottom. 1, 1, 0, 1, 0, 1, 1, 0. Base 2. 1, 1, 0, 1, 0, 1, 1, 0. Yeah, I wrote it right, I think. Okay. Now let's take a look at the answer. And see if I can remember how to divide by 2. And there it is. 1, 1, 0, 1, 0, 1, 1, 0. See, that's what I wrote right there. So that's correct. And so now you know how to get the correct answer on that stuff. So base 10 to base 2, repeated division. Sounds like a thing, right? Let's do one where the class tries to do it. I think that's very fine. And so what we'll do, this will be problem 3. Go to a nice dark marker. 27, nice low number, base 10. And now we want to convert that to some number in base 2. Who wants to give that a go? I don't know if you ever watch exercise videos, but if you don't do the exercises yourself, you really don't get the benefit. It might make you tired, but it doesn't really help you, especially if you're trying to get those abs. If you want those abs, you're going to have to do those crunches.
I think I got an answer here.
Okay, what you got?
Is it 11011?
That's what I got too.
Great.
I got the same thing.
Terrific.
Got that also.
So that is a correct answer. And I am going to quickly show you that's what we got. I put in the leading zeros just to be clever. In fact, if you think about it, the leading zeros don't really do anything because there's 0. But I put it in there just to sort of see if people were paying attention. So 11011 is exactly right. So that's cool. You guys are, you're doing it. So let's try and skip some of the other base 10 to base 2 conversions in the homework and move directly to something a little bit different. Let's take a fresh sheet of paper. And let's do problem 6. Actually, I'm going to change to a marker. And problem 6 says, convert the following base 2 number 0, 1, 1, 0, 0, 1 base 2 into some other number base 8. Well, it says over here that if I want to go from base 2 to base 8, I need to group by 3. So what I'll do is I will take my little blue pen and group by 3, starting from the least significant bit. And then I'm going to write down the binary equivalents. That's a 1, and that's a 3, base 8. And sure enough, if we take a look, That is a correct answer. Now the question is, how did Professor Lyon get 1 and 3 for these two symbols? And the answer is, well, if you take the octal numbers, 0, 1, 2, 3, 4, 5, 6, and 7, and write them out in binary by counting 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, you can see that 0, 1, 1 is equal to 3, and 0, 0, 1 is equal to 1. And this is the radix equal 8, and this is radix equal 2. And that's how you get that. So that's a sort of a good example. Let's try another one where you guys do it. I'm going to do, this is called question number 7. And in question 7, what we would like to do is take the binary number 11101 and convert it into base 8. And I'm going to let you guys try that.
Professor,
Yes.
I'm still a little confused on number 6. So we got the 3 and then we got the 1. So is it just 31 base 8?
That is almost correct. We would say 31 base 8 because 31 sounds like a base 10 number, but 31 is a completely different number than 31 because 31.
Oh, okay.
Yeah, that, I mean, it's a kind of a, I don't know. I'll try and be consistent in the course, but I don't want to start saying things like, 11,101 if I'm in a base 2.
Professor,
Yeah.
is it 3-5 base 8?
That's what I got too.
Great. That is exactly right.
I got that too.
You got 50?
No, 35.
35. Okay, 3-5. Yeah. We want to say 3-5 base 8 because 3-5 base 8 is a totally different value from 35, as you can well see. So let's see now. Maybe we'll do one more base 2 to base 8 example. We'll start with 1, 0. Oh, this is question 8. This will be a binary number, 1, 0. Excuse me. So what I have here is a binary number. I want an octal number. And what I really want is for you, the students, to try this because that's learning. If you can do it, then it's learning. If I do it, it's not learning.
I got 134 base 8.
That is correct.
That's what.
That is exactly right. And the way we do it is we divide into groups of 3. That's a 4. That's a 3. That's a 1. 1, 3, 4, base 8. You guys are getting it. This is good. So now we can do base 2 to base 8. That's good. How about if we want to convert from base 8 to base 2? That's interesting. So let's skip to question 11. So we're going to do question 11. We'll start with base 8, 4, 6. And we want to go to some number base 2. What do you suppose we should do? Well, let's take a look. What does our little thing says? Well, it says here we can go to base 10 And then we can do repeated division to get to base 2. But I don't like that. That sounds like a lot of work. And we did group by 3 to go from 2 to 8. Why can't I go group by 3 to go backwards? Can't I go like this? And the answer is yes, you can. And so how would that work? Well, take the numbers 6 and say that represents 3 bits. And there it is, 110. And here's another number 4, and that represents 3 bits, 100. And now we have the binary number 100110. And if we look at the answer, that's exactly what we see. And so what would happen if I said to you, oh, well, suppose this wasn't 4-6. Suppose it was 4-1 base 8. What would that be? Because we're grouping by 3, even though it says 1, we would use the leading zeros in the least significant bits. So we'd say 001 and then the 4, which is 100 base 2. You need to group by 3. So if you left off those 2 zeros, this would all be shifted over and you would have an incorrect answer. So from the point of view of group by 3, it works as long as you always make sure every octal, I don't want to call it a digit, but I guess it is. Every octal digit is represented by 3 bits. A bit is a binary digit. So that's a group by 3 solution. Let's do another one. This is going to be question number 12. What we want to do is take a number 74 base 8 and convert it into binary. And I'm going to let you guys try that. I think it's better if you do it.
I got 111100 base 2.
That's what I.
That is exactly right.
That's what I got too.
Cool. So that is, we'll validate that against the actual answer key. There it is. And you can see right in through here, if you take the least significant 3 bits, that's actually 4. And if you take the most significant 3 bits, that's actually 7. And we can see that. We can see 111 is 7. If we go over in here and we look, 111 is 7, 100 is 4. And so that works. You guys know how to do this, which is cool. You know, my spidey senses start to tingle when I can sense learning. So I think, look out, there might be some learning going on here. So that's good. Learning is good. That's why we're here. So let's see now. We know how to convert from base 8 to base 2 now. Let's see what other kind of base conversions we need for this homework. How about question 16? I'm going to skip ahead because that's a little bit different from what we've seen before. What we'll do is we'll write it out as base 8, the number is 27 base 8. And we want to know, how do we get the decimal number? How do we get the decimal number? So go back to my little summary. I'll go from base 8 to decimal. I need positional notation. So now I'm going to let you guys tell me what you think that number should be.
Is it 2, 3 base 10?
Yep, that's exactly right. And let's see how that happened. So that's 2 times 8 to the 0, 1 plus 7 times 8 to the 0. 2 times 8 is equal to 16. 8 to the 0 is 1. So that's 7 times 1, which is 7. And now we have 7 plus 16, and that should give us 23. Base 10. That's exactly right. That's how you do it. So you guys are doing it. That's good. Anyone confused by this? So we got pretty far along on this little homework assignment here.
Can you please just go over that summary quickly again?
Sure. So here's the summary. And what it says here is if you're in base 10 and you want base 2, you use repeated division. If you want to go to base 8, you start with base 2, you group by 3. If you want to go to, did we do base 16 in our little summary sheet? I guess I didn't write it out. If you want to go to, I thought I did write this out. Maybe there was a different summary sheet somewhere. Yeah, there it is. There it is. I did write it out. Right. So if you want to go from base 2 to base 16, you group by 4. If you want to go from base 2 to base 8, you group by 3. If you want to go from any base directly to base 10, you use positional notation. If you wanted to go from base 8 back to base 2, we use the group by 3. So we just make an inverted arrow. And in fact, we didn't show it, but if you want to go from base 16 back to base 2, you can do group by 4. And I can show that later. Got any questions? So then, an obvious question, I think, can I go directly from base 10 to base 16? The answer is yes, you can, but you have to divide by 16 repeatedly, which is a little less easy than dividing by 2, I think. I don't like to divide by 16 because my head hurts or something. Yeah, same thing. Dividing by 8 is way harder than dividing by 2. Because the answer is always 0 or 1, and there's always 1 or 0 left over. So that makes it easy. So we've done base 8 to base 10. We've done base 2 to base 10. We've done base 16 to base 10. Let's get, a lot of the homework is drill work, so you know how to do the basics now. And let's try base 2 to base 16. Well, I think we did that already, though. Well, no, let's do it anyway. We'll do base 2 to base 16, and this will be problem number 26. This is how far we've gotten already. So this is pretty cool, actually. So problem 26 says we're going to start with 1, 0, 1, 1, 1, 0, 0, 1, base 2, and we want to get a number base 16. And according to my diagram right here, I have to group by 4. And then I can go and look this up. and it's 9. And I can look this up, and it's equal to D. No, 1011 is B. So I have B9. It's like Battleship. B9, base 16. And if we look it up, what do we got? It's B9. How about that? So that's pretty cool. I got it right. Actually, if I didn't get it right, people should worry. So I'm going to have you guys do one because I think that's better. Better if you do it. Let's get a fresh piece of paper and let's try problem number 27. In problem 27, someone said, given 110, 11100 base 2, find the base 16 number. Okay, I'm going to let you guys do this one. And if it helps any, I'll
The DC.
DC is correct. That is exactly right. So that's DC base 16. And so what happened was we took 1100 and said that must be equal to C. I look it up. Yep, it is. And then D is 1101. And that's what we got there. So grouping by 4 and writing it directly through inspection. But first you might want to consider writing out this little truth table, which basically just counts to 16. Well, counts to 15 from 0 to 1111. And then assigns letters and numbers to each one of the bit vectors and gives you an opportunity to map the bit vectors directly into letters and numbers. And that is how you do that. Anybody getting a little bit lost? Shall we try one more? One more? No?
Yes.
Yes, let's do one more. We'll do one more. I think we have time. It's 1:42. I've got till 1:45. I'm going to do question 28. And question 28 says 0, 1, 1, 1, 0, 1, 0, 0, base 2 has to be equal to some number base 16. What could it be? I'll let you guys figure that out.
Seven, 4.
That is correct. That's exactly right. Here's the answer, 7, 4 for sure. And it's clear if you take the least significant 4 bits, that's 4. If you take the most significant 4 bits, that's 7. And that's 7, 4, which is exactly right. So you guys are getting it. Anybody confused by this?
No.
Okay, good deal, good deal. So I don't think we have any more time. I'm going to call it quits for now. We got up to question 28. Please keep track of that. We'll pick up this thread on Thursday. Take a stab at the homework. Read Appendix A and bring your questions with you to class on Thursday, and we can address any question you may have. And stay safe and enjoy the rest of the day. Thank you.
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 Thank you.